Hello, everyone. Now we come to broadcasting. The term broadcasting describes how NumPy treats arrays with different shapes during arithmetic operations. So arithmetic operations can still take a place between arrays with different shapes, but under some constraints, not always. Okay, so the smaller array is broadcast across the larger array so that they have the same, that they look like they have the same shape. So conceptually, okay, if you have two arrays with different sizes, take, for example, take like one array, take two arrays, they have the same number of columns, okay, but one has more, one has like a number of rows and the other one has only one row, okay. Then this one, the small one that has one row, I still can perform any operation between these two. For example, I can perform addition. Think of it as NumPy is replicating that row as many as the number of rows of the large one and then perform the addition. Okay, that's conceptually, okay? But actually NumPy is smart enough to do it without like consuming more computation or space, okay? So think maybe of it like taking this row and adding that row to every row in the large array. We're gonna come to explain the rule here. So the key broadcasting rule is when operating on two arrays, NumPy compares their shapes element-wise. So they have shapes. For example, if it's a 2D, then there is the shape has the axis 0, the value for or the length of the axis 0, comma axis 1, or the number of rows and the number of columns. Okay, so we can say axis 0, axis 1, number of rows, number of columns, or dimension 1, dimension 2. So you have those numbers, you have the shape information for the two arrays, then it will compare them element-wise. Okay, now it starts with the trailing dimension. It doesn't matter from where it starts, but actually it compares these numbers element-wise. If they are equal, okay, if they are equal or one of them is 1, then the operation will take place. It will be performed no matter what the operation is, addition or multiplication or whatever. Only under this rule, if for every dimension the values are either same or one of them is 1, then the operation will be performed. Otherwise it will not. Okay, so maybe, yeah, let me read through these two lines before we go to the example, because examples will make it more clear. So think of it like as a way, like if I have one row, I need to add it to every row in an array, then I don't need to do a loop. I don't need to repeat it, fill a matrix or like repeat that row. Just add that row to the larger array and it will be added to every row in the larger one. So what's happening behind the scene here, if the arrays do not have the same dimensions, okay, so one of them is like for example, and if like take a 2D array where in the first dimension they are equal, but in the second dimension like they are not equal, one of them is 1. Or take the example where actually I have 2D array and I want to add 1D array. So I want to actually perform operation addition between a 2D array and 1D array. Okay, since the second one is a 1D array, then what happens here, we pre-append the shape of the lower dimension array with ones until both arrays have the same dimensions. So I think by example, maybe because explaining it from the text will be difficult. Let's look at the examples. The examples will make it so clear to us. Okay, let's start with this very simple example here. So we have two 1D arrays. Okay, so here they have only axis 0. So there's only one axis. There's only one dimension. Sorry, and that is the only axis, and that's the trailing axis. There's no other axis. Axis 0. Okay, and in axis 0, the dimension is equal for both of them. Okay, both of them have 3 elements. Okay, so now if we run this cell. So what we are doing here, we are performing addition and multiplication. So that takes a place. So here we have, this is the result of the addition. It's an element-wise addition, and this is the result of the multiplication. So element-wise multiplication. So since they have the same number of elements on that axis, which is the only axis they have, axis 0, okay, So then the operation will take place. Okay. Now let's assume like this one has only 2 elements and this one has 3 elements. Now they have in that axis, okay, they have different number of elements. Both of them are 1D here. They are still 1D, but this has only 2 elements and this has 3 elements. So so if we print out the dimension here, let's look at the shape. Okay. So look at the shape. The value of this shape is 2 and here is 3. So they are different. Okay. So the rule is not applicable here because they are different and and the smaller one is not 1. It's greater than 1. So the rule is not applicable because the rule says the addition or whatever operation will take place if they have the same number of elements. Okay. Sorry, the same value. Okay, the same length for every axis, or if there is a specific axis where they are different, then one of them should be 1. Okay, and that's not that doesn't hold in this case, so that's why we have an error here. Okay, it doesn't hold for this case. So now if we reduce this to only 1 element, okay, now this is 1 element. Now the operation will take place because they are not at the same. So for this axis 0, which is the only axis they have, both of them are 1D arrays. They have only axis 0. Okay, and so now if you look here, they are not equal, but this has a value of 1. Okay, so then the operation will take place. Think of it as this. Python NumPy is replicating this 0 3 times and then performing the addition. The result is the same here. Okay, or otherwise, or you can also think of it, and this is what exactly happening here. It's broadcasting this over this array. So it's adding this element to every element here. Okay, it's taking this element and adding it to every element here. Okay, because the rule is up now, the condition is satisfied. Now let's take this here. Let me comment this out. This is a 2D array. Okay, let's take this one. Okay, we have the first array is a 2D array. Okay, we call the function ones. So it's a 2D array that has 2 rows and 3 columns, and the values of the elements are all ones. Okay, and this one is a 1D array. Okay, so we're calling the function aRange to generate range. Okay, starts from 0 to 3. 3 is not included. So there will be 3 elements, 0, 1, and 2. aRange is equivalent to the function range, the Python built-in function range that returns also range. If you use that function instead of this, you will have 0, 1, and 2. But the return object there for that function is a range. Here, the return object is an NumPy array that has 0, 1, 2. So it's a 1D array. So now we are performing an operation between 2D array and 1D array. Okay, so there is 1 row here, and we want to add that row to every row in this one. Okay, so now they are not of the same shape. Okay, so what happens behind the scene? So 1 is appended here, as it's explained here in this text. Okay, so then the sizes will be, so now if you like, the size of this is 3. The original size is like this. It's 3, comma. That's it, right? So we're appending 1 here. Think of it as this, what's happening. 1 is appended here. So now this became, the shape information became 1, 3. This is 1, 3. And this one is 2 by 3. This is 2, 3. And this is 1, 3. Now make the comparison. This is 3 and this is 3. The axis 1, or the column axis, okay, or the column dimension, because we have rows and columns. So this is axis 1, or the number of columns, okay, or the second dimension. All these words you can use it for it. So the second dimension here, okay, for this and this, they are equal, okay, and this is the first dimension, okay, so they are not equal, okay, they are not equal, but this one is equal to 1. So then the rule is applicable, so the addition or multiplication or whatever we perform will take place. Okay, this is the first one. It's a 2D array. This is the second one. It's 1D array. Okay, but think of it as like this row is replicated. So we have another row below it with the same values, and then the addition and multiplication are performed. So this is the result of the addition, and this is the result of the multiplication. As I said, you can think of it as this row has been replicated first, and then the addition or the multiplication is performed, or think of it as this row is added to this row, and then added to this row for the addition problem, and multiplied with the first row, and then the second row for the multiplication problem. Okay, now let's take the second example here. Okay, so we have this. Okay, A is of size 3 by 4. Okay, so we have 3 rows and 4 columns for the first array, and for the second array, the size is 3 by 2. So both of them are 2D arrays. Okay, but the shape information are different, the number of rows and columns. Okay, the values or the length of the first dimension and the second dimension are different. So I'm writing them here under each other to make the comparison. If you look into this here, this is the second axis, the column axis. Okay, so as you can see, these numbers are not equal. So we have here number of columns is equal to 4, and here number of columns is equal to 2. Okay, so then we will have an error here. We will run into an error because the rule is not applicable. So this has to be either 4 or 1 in order for addition or the multiplication to take place. So we will run into an error, as we can see here. Okay. Okay. Now let's go to the last thing here in this topic, the Python review topic, the masking. Okay. Masked array is an array of booleans that determines for each element of the associated array whether the value is valid or not. The masked arrays are obtained using different conditions, and their comparisons are vectorized as well. So what do we mean by this text? Let's look at this example. This example will make it clear. So here we are generating this NumPy array, okay? And I added this here, these lines. So let's first, let's look at, this will make the explanation even easier. So now, this is the original NumPy array we created. So now we are creating a new array using this line here. So A is equal to X less than 3. So what's that supposed to mean? So A is an array of booleans, okay? So whenever this condition is satisfied, so there's a vectorization wrapper here, okay? So this condition will be checked for every element in X, okay? Wherever this condition is satisfied, the corresponding value, the value of the corresponding element in A is true. And whenever this condition is not satisfied in X, the corresponding value in A will be false. For example, this condition is satisfied for the first 2 elements. So the first 2 elements in A, each one of them will be true. The value of it will be true. And it's not satisfied for the last 4 elements. So then the last 4 elements, the corresponding value in the new array A will be false. So if you print A, this is what we get. Okay. True for the first 2 elements and false for the remaining 4 elements. Okay. So we are reprinting again things here. Okay. So print X less than 3, print X greater than 3. So the idea is same. So for example, if you take this one, X greater than or equal to 3, okay, then when X is greater than or equal to 3, it's false for these 2 elements, and it's true for the remaining 4 elements. So we have 2 falses and 4 truths. Okay, this masked array is useful when you want to extract a specific slice from an NumPy array, a slice that satisfies a certain condition. Then you can define this array of booleans by defining your condition. For example, here mask is equal to X less than 3. Mask is an array of booleans. You pass it here inside the brackets, okay? And then you extract the slice from X that satisfy that, where you extract the slice from X where the slice that like the elements that satisfy this condition. So the ones where the value of mask is true. Okay. So for example, here x less than 3. Okay. These two elements satisfy that condition. The remaining elements do not satisfy that condition. So then mask here will have mask will actually be exactly this one. Okay. So true for the first two elements and false for the remaining 4 elements. So when we pass mask here, then which slice from X we are extracting, mask is true only for the first 2 elements. So then the return of this one, X of mask is equal to 1 and 2. Okay, that's it. It's a NumPy array, including these 2 elements, because these 2 elements satisfy this condition. Okay, and you can build more complicated conditions like this one. For example, mask is equal to X greater than 2 and X less than 5. So which slice satisfies this condition? Which slice satisfies this condition? It's this slice, right? So then 3 and 4. Okay, so then the return of this will be 3 and 4. An NumPy array that contains only these 2 elements. You can look at this yourself. It's the same idea. Yeah, so I will come back to this. Let me talk about this because it's in the same topic, the masking. So here you can also pass a 2D array, okay? And then you check for a specific, here you extract a slice based on a specific condition. For example, the condition here is m is greater than or equal to 6, okay? So then the elements that satisfy this condition are 9, 6, and 8. So then the return, the output A, will be 1D array that contains these 3 elements in the same order they appeared at here. So 9, then 6, then 8. It's a 1D array. Okay. Though the original array is 2D, but here the extracted slice is 1D array. Now let me come to this example. This actually, it's not about the topic we are covering today. It goes all the way back to the use of a split function, okay? But it's good to explain it, okay? So here we are generating like a 2D array of size 4 by 4. It has 4 rows and 4 columns. So the elements are the integer, randomly generated from the integer numbers between 0 and 9. So each element here in this 2D array is a random integer number between 0 and 9. Then what we are doing here, this is A. Okay, then we are, what are we doing here? B is what? So we are splitting A, okay, along the axis 0, the row axis. So we are splitting the array into how many arrays? That depends on the here. What are we specifying here? So we are splitting along the row axis, okay? And we are actually passing the index where we split. So here inside brackets, we pass 1. So we are splitting at the row with index 1, which is the second row. Okay. So then the first row will be in a separate array, and the remaining 3 rows will be in another array. Okay. So there will be 2 subarrays, array that contains the first row and another array that contains the remaining 3 rows, okay? And now up to here, okay, we did the splitting. Here we are accessing the first subarray, okay? And we are printing both the original array as well as the first subarray after splitting. Now, what will be the output of this line? What will be the shape and the size of the first subarray? So the shape is going to be what? It's one row, okay? And it has 4 columns. So the shape will be 1, 4, right? Because the first row is in the first subarray, and the remaining 3 rows are in the second subarray. So the shape of the first subarray is 1, 4. Though it has only 1 row, but it's a still 2D array. It's a still 2D array because the original array is a 2D array. So it's a still 2D array. It's a 2D array that has only 1 row and 4 columns. So the shape will be 1, 4, and the size will be 4, right? The total number of elements is equal to 4. So this is it. This is the original array, okay? And here is the shape information, shape and size information of the first subarray after the split. And here is the subarray, which is 1 row. As you can see, we have 2 brackets here, okay? So it's a 1D, it's a 2D array that has only 1 row, okay? Now, if you want to access the second subarray, we can access it by passing index 1. It's the second subarray, okay? So we change this index to 1. What will be the shape of that? It will be 3 by 4, 3 rows, 4 columns, and the size is equal to 12. So if you print out, this is it. The shape is 3, 4, and the size is equal to 12, which is the total number of elements. And here it is the remaining 3 rows. So the last 3 rows, okay, of the original array. With that, we come to the end of this lecture, and I'd like to thank you for watching. Thanks.